Hello, everyone. Welcome back. Today we're going to be discussing the definition of a derivative. Now, as all of you have started to learn in calculus, a derivative is a slope of a function at a specific point. So it is the slope of a tangent line. Here on the right-hand side, I have drawn a parabola, which is the example we will be going through later. And we will be, as you can see here, we have a selected point. We'll make this point 2. And we can see that we've ran a tangent line through the point 2 on this parabola. Now, I think everybody should know at this point, tangent means it touches at one point. So this slope is specifically tailored to this one point on this graph. And if we plug in any other point, for example, if we plug in, let's make this 3 here, this would be the new tangent line. So the slope changes with respect to where we are on the graph. And that is why we need a derivative, because we cannot find the slope of these functions through customary forms such as rise over run. These are not linear functions. So here at the top, this will be the formula we're using to solve the definition of a derivative. It is in essence a limit as h approaches 0 of f of x plus h minus f of x over h. Now, the reason we are using a limit here is because we are getting closer and closer to 0, or our point here. And if you guys have seen, we use something called secant lines. I'm going to be drawing a secant line here where we open at 2 points as opposed to 1 point. And we're looking for maybe this point here. So we changed our secant line and we keep getting closer and closer to the obtained value until we are eventually a tangent line, which is why we are saying we're approaching 0. H is this point that we're breaking into. So secant lines open up at 2 points, tangent lines touch at 1 point. So that is why we're using a limit, because we are wanting to get closer and closer to becoming a tangent line. Now, to use this formula in an example, we'll be looking at x squared. Now, everybody probably knows how to use the power rule for derivatives, so we already know the derivative of x squared is 2x. So this is going to be a useful way of checking and making sure that we're using the definition of a derivative correctly. Now, once again, I've plugged the definition of the derivative here, and for h, I've put it here, and we have our formula, which is x squared. So we're going to be plugging in an h with every x. So we have x plus h squared instead of just x squared minus f of x, which is x squared, divided by h. Now in the next step, I've performed some foiling and I've expanded to make it x squared plus 2x h plus h squared minus x squared all over h. Now, as you can see, we have a positive and negative x squared, so we're going to quickly cancel those two out, which will give us 2xh plus h squared over h. Now, in the next step below, what I have done is I have pulled one h out of each of these because they are like terms. So I made it h times 2x plus h. And once again, we can cancel out an h here, which leaves us with the limit as h approaches 0 of 2x plus h, which, if we plug in a 0 for h, will just be 2x plus 0, which gives us 2x. Now that is the derivative of x squared, and as I said before, the slope at a specific point of a parabola is going to change with depending on what point you're talking about. For example, if we are at 2, we will have a slope of 4. If we are at 3, we'll have a slope of 6. If we're at 4, we'll have a slope of 8. So this is kind of how we solve for specific slopes of specific functions that are not linear. I hope this has been useful in teaching you how to use the definition of a derivative.